All right, here we go.
Okay. Good afternoon. I'm PCI Executive Director Kevin Corson. Thank you for joining us for the Infrared 101, how it works and when to use it to make money. The webinar is presented by Marty Sawyer, owner of Trimac Industrial Systems and Protherm. Before we get started, I'd like to remind everyone that all attendees are on mute, so if you have any questions along the way, please type them in the Q&A panel. Marty will address the questions at the end of the webinar. If we run out of time, you'll receive a reply via email from the presenter after the webinar. After today, this webinar, which is being recorded, will be available through the PCI store within 5 to 7 business days, which can be re-reviewed. All attendees will receive a brief survey after the webinar. We appreciate your feedback as we continue to offer a variety of educational programs and always trying to make improvements. Please take a few moments and reply to the survey. Now I'd like to introduce the presenter of today's webinar. Marty is CEO and owner of Trimac Industrial Systems. They manufacture ovens, washers, and infrared systems. Marty recently added the brand Protherm as the electric infrared component to Trimac's gas catalytic and convection technology. Marty, take it away.
Thank you, Kevin. I am very happy to be here, and it is a great afternoon. I am not seeing myself in there, so I'm hoping I'm in the center. I'm still seeing Kevin's thing, but let's get started. So I started this speech a couple years ago when I tried to teach myself more about infrared, because the question I always had was, if I don't get it, then certainly my customers can't get it. And the information I found on the internet and in our own website and competitors' website basically left me a little bit confused about how the technology of infrared actually works. So I started doing some research, and thereby that is how this speech originally got started. So the first thing we always start with is the science of heat. Basically, what is heat? So heat is energy. So we think about energy, the heat hits organic matter that it touches. And that's what makes the molecules move. They go back and forth, and they go back and forth, which creates the chemical reaction. And that's where, excuse me, where the energy is created. Sorry about that, I got a little fast on me. When we think about how heat is actually transferred, we have 3 main areas that we use in powder coating. So conduction is really the most common that we don't really understand. And that is the touching of something. That is, the heat is transferred by direct contact to solid matter. So when you put a hot poker in a fire, sooner or later, your hand's going to be hot. Convection is the movement of air or fluid, which is the one we think of the most often. And then radiation is the heat transferred by electromagnetic energy. And when we look at organic matter, because that's really what we're dealing with here, is we're dealing with solid things that we are trying to heat up. And if we start on the left side and think about the item on the left being a hot cup of coffee sitting on a table. And as time goes on, that coffee gets cooler and cooler until it is room temperature. We always hear about room temperature. Well, that is what thermal equilibrium is. So basically, the energy in the coffee, that molecular energy in the coffee, gave its heat to the room by 0.00000 some degrees and made the room a fraction hotter, because the thermal energy from the coffee went into the room, the cup, the table that it's sitting on. And that is how parts actually get hot. Convection is the one that we think of the most. That's the one that is ubiquitous in our industry and the ones that we see most often. And again, it's that air movement. So when the air molecules are heated, they expand, and that's what causes them to go lighter. And that pushes down the heavier ones, which fall to the ground. And it is that movement of air that puts that hot air around our parts. Same way when you boil water, it's the same concept. So conduction, as I use the hot poker example, conduction is the medium of moving the heat through a solid. So when we think about the real heavy parts that we're trying to heat up, we've got to conduct the energy from the surface all the way through the part. That is conduction. It's a very important piece of heating parts that is often not really considered in the process. So radiation, by another example, is looking at it's either absorbed into the part. If it's glass, it theoretically go through the part, glass, plastic, anything that's translucent, it can go through the part, or it can be reflected. So if you think about sitting or standing on a hot driveway in the middle of summer, how hot your feet are. And even on a 50-degree day, that driveway with that hot asphalt will still be hot. But snow, it can be 20 degrees out and you can get a sunburn when you're skiing. And that's because that energy is reflecting off the snow and hitting your face. So that kind of gives us a good example of how radiation versus the absorption. What we're always trying to do with infrared energy is get the energy to be absorbed into the part, because anything that's reflected is theoretically wasted energy. So as we said, absorption is the key. That's really what makes the biggest difference about all this. So when we think about organic matter, and absolute zero is when there's no molecular movement. So all organic matter is going to absorb and emit infrared radiation. So a white body is where you have zero absorption and you reflect 100%. A black body is where 100% of the energy goes into the part or gets absorbed into the part. So when you think about wavelength, which we're going to talk about a little bit more, you want to ideally match the wavelength, and it's not an exact science like some people might get caught up in thinking. It's more of a range, and the wavelength is what maximizes the absorption. So when you're outside of that range, you get more reflection. So you lose some of the benefit of that energy. So as we talk about that energy, electromagnetic, and you guys have probably all seen something kind of similar to this, and this is just understanding the range of infrared, that it's at one end is visible light, and on the other side is UV. But one of the things that I think is very important to know is that there's no magic between long, medium, and shortwave. These are arbitrary breakoffs that I have no idea who actually did that, but somebody put that in that way and said, this range is long, this is medium, and this is short. But the infrared energy itself, when you stand in the sun and feel heat, that is infrared energy hitting you. Because right when you move into the shade, all of a sudden you're cool again because the infrared energy is blocked. So infrared energy is basically just like putting the sun on your part. And how that infrared energy is generated is it's basically going to come through the electrical grid or with a gas catalytic, the chemical reaction that is basically the same technology as a catalytic converter in your car. But that's where a lot of this technology has gone to. Also, thermal oxidizers is the same technology. So let's talk about wavelength a little bit, and let's delve into that. Wavelength actually equals temperature. So the higher temperature you have, the shorter the wavelength, and you get more power and speed. And that's what's really important to understand. The problem with more power and speed is the flexibility goes down. So there is a direct and inverse relationship to the temperature and your flexibility. So absorption on most organic matters that we use in powder coating is optimized at lower temperatures in the long to medium. But as you get higher, higher into the medium, you tend to get more speed, more power, but the trade-off is always the absorption. So that's a little bit of the dance of working with a good vendor who understands their technology. So this is a chart I made that I think is really important to understand because, again, there is no magic between short, medium, and long. It is a range. It is a curve. So as you look at the temperatures, you can just see how the different parts are being arbitrarily set, but the curve itself moves through the range. So as we look at each individual type, you've got shortwave, which is typically a bulb technology, and you can see those temperatures. Medium wave can still be a bulb. It's often electric resistance elements. And then long wave is typically gas catalytic in what we do for a living. And those give you the temperature ranges. And as we go through each type, you've got convection and thinking about that temperature. So you're going to basically, electric can go lower than 250, but gas is going to start at about 250 and you can go up to 500. The pros of convection, it's very easy to work with. It is very flexible. It is the industry standard. You can find a convection oven manufacturer, they're ubiquitous. The problem with convection is it is a higher technology to operate. It is the slowest. It is inconsistent. You've got environmental concerns. You have that dust moving around that is in the airflow that affects the quality of your finish. And it is a space hog. It is by far the biggest space hog, but it is easy. So it's always a trade-off. When you get to gas catalytic, long to medium wave, the pros and cons is gas catalytic is always going to be the cheapest to operate. So your cost per piece is going to be lowest in this technology. It's going to be, you can cure a complex part with gas catalytic. You can even do a job shop in gas catalytic. There are environmental benefits. Again, it's like a catalytic converter. And you can put this in a paint environment or any other explosion risk installation. You can do class 1, div 1. And it actually uses the VOCs just like the natural gas that has fuel for the part. And it won't, however, suit every part, like all infrared will not suit every part. And this one is probably the hardest to operate of infrared. So it's got a bigger learning curve than electric. And it's typically the most expensive on the front end. It's going to be at least a 10% premium, typically the trade-off, but it's about what's important to you as to whether that trade-off makes sense. When we get into electric, and I have grouped them together because typically shortwave applications are operated at lower temperatures in powder coating. So they're typically operated more in the electric medium wave temperature range. So we're just going to look at it as one grouping. So the pros, it is by far the fastest technology. You can get instantaneous reaction it's all down to seconds. It can create very uniform heat distribution. And obviously, since it's working off the electric grid, you have no products of combustion. You are not doing anything with fossil fuels. So if that is a primary driver, that can be a really great technology for you. Downside is obviously it is expensive to operate. It is to get a BTU into a part, even though BTU is typically thought of as a gas measurement, it's still a heating technology. It is going to be expensive depending on how much power you're going to need for your part. It can be unforgiving. The higher temp you go, the less forgiving it is. So you have, you've got a lot of gears, but you've got to be able to use them for your part. And it also has a learning curve. You're typically not going to cure with electric. You can when you have one part and you can design the oven for that part and it's a certain type of shape. But typically curing is done with catalytic in the infrared scale. Controllability. This is really the sweet spot of infrared that people don't always understand what value this can be, because you can zone to every heater theoretically. And when you're in convection, you have one temperature to work with, and that's what the whole oven is going to be. And you can turn it down into your low fire, but that's going to be a slow, arduous, and very non-responsive way to control temperature in an oven. It's a way to save gas, but it's not really controlling the process very well. But all infrared can be zoned. You might zone top to bottom because, again, heat rises. So maybe you don't want as much infrared energy at the top to get more uniformity. You might have a little more energy at the bottom. You may hang your parts differently, where you put your heavy parts at the top and then you put your light parts at the bottom. There's lots of ways to do it depending on what you're doing. You also can zone front to back, which is basically the idea of a ramp and soak. Basically, you can do that through your zoning, or you can do a soak and ramp, depending on if that's what you're doing. You want to do a slow curve up for the parts. And also the temperature level, so you can zone it. Then you can also affect the temperature of the heaters to where you can have so much response in the heaters themselves to modulate as may be required by a different grouping of parts. Some parts, a big heavy part is going to need a whole lot more energy than a piece of sheet metal. And in some companies, you're putting both of those on the same line, and you need the ability to be able to moderate your energy level per the part. So when we talk heat uniformity, so this is something, for instance, like in composites where heat uniformity is so critical. Convection, you certainly can get to plus or minus 5 degrees, but you have to do some extra design and cost. 10% or 10 degrees is typically the norm for a quality oven. Infrared, you can have, depending on how you design it and depending on what you're trying to do, you can get almost 100% uniformity across the part. And that is important to know, that is a function of the design. Infrared is designed. It's not the same as convection where you just put it in, ding, I'm done, and you take it out. Infrared does not work that way. It is more complex. So when should convection be the optimal choice versus infrared? And obviously the ease is always going to be the main driver. And when we look at when you have a huge variability of parts, certainly convection can be the best choice. And like I said, it's easy. And one of the things that people don't always understand is if you have dual lanes, typically you can't use infrared because it can't see the other side. There's some things you can do to work around that, but typically dual lanes are going to always be convection. So infrared versus convection, control, uniformity, I mean, a lot of the stuff we're talking about, you typically, because you can do the process so fast, you're going to see some operating cost savings. And that can factor into your space, throughput, your work in process. So theoretically, if your oven is 1/3 shorter, 2/3 shorter, 4/5 shorter, whatever the case may be, depending on what you're doing, that's how much less product you have on the line at any given time. And that work in process can be substantive to the value proposition. Quality will always be better in infrared because you're not introducing the air into the process. And environmental, we've already talked about that. So when we get to the proof, this is my favorite picture I've ever taken. It's with an infrared camera, obviously, and you can see the part heating. This is just entering the oven. I was just at some job shop we were at, and I had the camera with it and I took this picture. So you can see the part as it's seeing the energy begin to heat up. And then you have the light purple and then the dark purple. And that is the conduction going through the part that the infrared energy has not yet seen. But the conduction is already affecting the rest of the part. And I think, you know, sometimes you have to see it to really see what infrared can do. So this chart is to show, you know, I call it see the cure. So at the top picture, you can see that these are blue boxes hung up going into an infrared cure oven. And this is a catalytic. And if you look at the bottom, it's 3 pictures side by side spanning 35 seconds. So the first picture, the last picture is 35 seconds after the first picture was taken. And if you look at the third box in, that you can see the purple changing, and then the middle picture and the farthest right picture, you can see it go from purple, dark purple to orange, showing you the heat being absorbed into the parts. So I have not yet had an opportunity to take some parts and do it in all the technologies and use one part and use a part like this and do oven monitoring of these type of parts against all the heat technology. It's on my to-do list, just haven't quite gotten to it yet. So if you want to send me a part, I'll do it. But anyway, This part, you can see where the measurement devices were put on. And here is the oven monitoring on showing how it came out in a catalytic oven. And as you'll see here, the next slide is going to be the convection. You can see the movement. Same part, same powder, same process, and that is how much faster. If we were doing, if we were doing this in electric for a boost or whatever, that curve would be dramatically, again, shorter to the left. So here's the results of that. A little over almost 7 minutes versus 30. So that was a dramatic difference to get to a target of 325, which is what the standards of that particular test was. The environmental impact is when we are thinking about using fossil fuels in our industry and what happens to the environment. First of all, you have the burning of the fossil fuels. So convection is an incomplete combustion process. So it outputs CO and NOx. In a complete combustion, where the chemical reaction of combustion completes its cycle, the natural gas, the CH4, is going to all end up as CO2. In catalytic, because you're using about a third of the natural gas, your net CO2 is significantly lower. Our calculations show around 50% reduction in the CO2 levels. In electric, obviously you have none. But then there's this other piece, which is the air. So when you think about these pictures, the picture on the left is a catalytic oven stack, and you can see at the very bottom level, at the highest level, it's at 194 degrees. And at the top, it looks like it's maybe 100. Then you see the picture of a person's hand over that. So it felt like a gentle, warm breeze coming out of that stack. So there's very little air moving, because catalytic ovens typically have a variable exhaust. The bottom right picture is a convection stack, and this is in the exact same location, same company, operating on the same day. And the air volume's coming out at about 350 degrees. You could not get anywhere close to it. And the amount of sound coming out of that stack was enormous. So it really was a great demonstration to me of how much air we are throwing into the environment in convection from an environmental standpoint. So not only, that's one of the reasons why you have to, you have to put so much air into the ovens, is because you're exhausting at such a high rate, because you have to get all the CO out to meet NFPA. The volume of heat as well that is wasted going up the stack, because you can't use that for your process anymore. You heated up that air and then you threw it out into the environment. So that's one of the things to think about from an environmental standpoint. What we are seeing is companies are just now at the point where the environmental piece is more than just icing on the cake. That companies are actually starting to make decisions based on the environmental impact of the equipment they're putting in. But it's been a long time coming. So when we think about real world applications, excuse me, this is where, how can you use infrared in your application to make money? So the ideal implications or applications for infrared is heat sensitive substrates. It's, those work so well with infrared. And if you've been following the industry, MDF, hardwoods are using, have some new technologies on the powder side that is allowing that space to be sought to be a large growth market for the powder industry, because we have a whole new set of substrates that we can now powder coat successfully in production. They do require infrared to run these powders, but what you're looking for in a heat sensitive substrate, because it could be something more than just the substrate is sensitive, it could be the component itself is sensitive, such as a cylinder, where the internal seals have to be protected from the exterior heat. You can't use convection because you can't get them to the temperature that you have to cure the exterior of the cylinder to. You have to protect it. Infrared can gel that powder and cure that powder fast enough that before the heat can conduct into the interior of the part. But you also have glass and plastics. Those are also substrates that are starting to be powder coated, that infrared is a great technology for those. You also have some heat insensitive substrates, you know, sometimes like composites, fiberglass, and glass for that matter, that infrared can help you control a little bit more. Obviously, boosting is becoming more and more common. It is a great way when you just need to go faster. And we'll talk about that a little bit more. Two-coat systems where you want to gel the first coat before you apply it again. A small infrared oven can be put in the line and can boost that part and gel the powder so that you can do your second application. Sometimes you just want to preheat, you want to do a mill build, and so you need to get the part a little warm before you go through the application. Sometimes, you know, that's a great technology for infrared. We've done some infrared systems where people say, I've only got 3,000 square feet. That's all I have. What can I do in that? If we were to look at convection, they can't fit it in. But with infrared, you have the option of actually being able to do a throughput and have options to flow through without in a very limited space. So we talked about the speed side of how much the work in process changes and how much your throughput. If you have a situation where your line just can't keep up and you just wish you could get a little bit more, as long as your washer can handle it, you just add infrared to that convection oven and you will be able to go faster. If your convection oven is your bottleneck, infrared is the answer to that. You can put a boost inside the oven or the exterior of the oven, depending on how it's configured and space available and those kind of things. When we look at what types of heat to use, the things I always like to talk about is the 3 Ps. So the part, what is your part made of? Is it aluminum? Is it steel? Is it wood? What is the part made of? What is the profile? How is it shaped? A sheet metal obviously is going to absorb energy and love infrared and be easier to work with than a complex weldment. So the profile is very important. Then we get to the process. Running at 3 feet a minute is a whole lot different than running at 18 feet a minute. And your options and how you design ovens and what you can do is a function of the line speed. So how you're doing your process, how you're loading, unloading, all those things factor into infrared, because infrared is not going to be something you're going to buy used and just be able to put in. It needs to be designed for your line in your application. So this is getting a little bit more tactical on convection. So when you want the maximum flexibility, you're going to do all kinds of different parts. So some of this we talked about earlier in the other thing, or the other slide. Sometimes the issue is the way you're loading. And excuse me. If you have restrictions on how you're going to load or kit your parts, possibly on a line, that may make convection your best choice, because you need that flexibility, because of your lean initiative or whatever you're working on requires you to load in a certain way. Convection may be the best option. And it is, again, a ubiquitous technology, and it's proven, and you know how it's going to work. So catalytic, when someone comes to us and says, we're not sure what we want, tell us what's the best option. And one of the first questions we always ask is, is the cost per piece the driving issue here? Typically, business owners tend to be more driven towards that, where large companies' throughput sometimes is the most important driver. And there's no right or wrong answer to any of these. It is what's best for you. So if cost per piece is important, catalytic may be an ideal option. And when you want a little bit of a balance, you want some speed of infrared, but you still need more flexibility, and it's softer because it's lower temp. Again, the problem is because it's softer because it's lower temp compared to electric, it's not near as fast. So when we get to electric is a Ferrari. I mean, there's just no other way to put it by comparison. It gives you so much speed and so much control and so much ability to vary what you're doing and control how you deliver the heat, where you deliver the heat, when you deliver the heat. When those things and that throughput issue is the most important thing, electric is often by far the best choice. If you have gaps in the line a lot and you want to turn the heat down, electric is often the best way to do that, because you can get the part back up to temperature so fast that if that's a problem, which for some companies it is, if you're operating at very fast line speeds, 20 feet per minute, you're not going to use catalytic in a 20 foot a minute line. The conduction part of catalytic doesn't have time. The oven would be so huge. So catalytic tends to not do well when the lines go fast, because the oven increases in size and it becomes cost prohibitive. However, but if you can't use electric, and convection is going to be even bigger still. So again, it's always a balance as to what are the driving factors for a business that helps them figure out what they think is the most important issue to make a decision. I want to talk about air for a second, because I'm not just talking about convection air, I'm just talking about the air, because you're in an oven, whether it's an infrared oven or convection oven, and you're doing metal parts, things are going to get hot. The heaters will heat up, the heaters will heat the other heaters, the conveyor will heat up, the parts will heat up. There will be convection heat in any infrared oven. The question is there air movement? Air, in a complex part, people always think that you need convection because you got to get inside those hidden recesses because infrared can't see it. Well, what happens is air actually will swipe past those inside corners as well, just like the Faraday effect in spraying powder. The difference is in convection, the whole part is going to heat up. So you're typically curing those parts on those inner corners from the inside out, because it is the conduction that's finishing that cure, not the hot air, because air does not turn corners and go inside. Unless you force it in there, it's going to swipe past those. So it is important to understand that, because people talk about line of sight so much that is a limiting factor, and it can be. Again, it's a function of how your oven is designed and what parts you're putting in it. But air in electric resistance elements, for example, will actually cool the elements. Air, like a billow on a fireplace, will heat up gas catalytic. So air is a wonderful combination with gas catalytic, not always a wonderful combination with electric resistance elements. Bulbs, not so much, but you just don't typically see a lot of air movement in bulb-driven ovens. But when we talk about why you can cure complex parts with catalytic, it's because air can be that balancing medium for the complex part to drive the conduction in that much farther, and as well to cool the thin portion. If you have thicks and thins on a part, to cool the thin portion so you can keep delivering energy to the thicker part of the weldment. So thinking about infrared efficiency, because over the years someone said to me, well, this type of heater is the most efficient heater there is out there. And I said, well, how do you define efficiency? Where is there a chart that I can look at that says what this efficiency, infrared efficiency, actually means? So we're going to talk about that here in just a second. But in this vein, what we're talking about is electric typically has the highest efficiency of converting the input of electricity into infrared heat. So it works the quickest because of that high temperature. And that's where we get that control. Catalytic has a lower temperature and efficiency to the infrared heat because it produces also convection heat, but heat is still heat. So you can still use that. When you get into bulb technology where you have a lot of light energy being created, that light energy is actual waste. You can't use that for anything in the process. But since we don't operate at those temperatures in powder typically, that doesn't typically come into play, but it is important to understand we have the efficiency of the power source going to the emitter, and then you have the efficiency coming out of the emitter, the heater. So I define I looked this up, energy gain divided by energy used. I mean, the basis of efficiency. And I look at it for infrared and say it's speed divided by cost. How fast do you want to go and how much money are you willing to spend to get there? Because higher speed costs more. It's just as simple as that. So how do you balance that out? So to understand that cost benefit analysis, you've got operating costs, your first cost, your cost per square foot, the time on the line, and the control of what you're trying to do. All those things factor into what are you trying to achieve and how much money are you willing to spend to go there. Because sometimes in electric, if it's designed right, the process is so fast that it actually isn't more expensive. But again, it depends on what you're trying to achieve and the parts and the profile and the process. So when we look at trying to define a heat type, the 3 Ps, response time. Do you need instantaneous? Typically in powder coating, instantaneous is not really required. That's typically getting into thermal processing where you need an uber level of response. Typically seconds is more than enough for most powder coating applications. What kind of parts you're doing, the heat sensitivity, all these things factor into it. Sometimes people don't have natural gas. They're using propane. Maybe they're using all electricity. How much electricity do they have to have? How big is their incoming power? All those things factor into deciding what is the best technology for you. And obviously, first cost is a factor. And if one technology is going to be more expensive than others, payback, it's relative to how often you use it. I mean, there will be a payback in catalytic versus electric always on operating costs. But the question is, depending on how you're using it, when will that payback be, and is that going to fit your ROI in making a, typically what we see is it's anywhere from 6 months to several years, depending on how it's designed. So that helps people try to figure out what makes the most sense. So the specific things, as we drill down into the decision-making process, these are the kind of things that you can be thinking about. We've talked about most of these, but these all are business decisions. And people sometimes try to find the perfect technology, forgetting my business may be different from your business, and thereby there are other factors that need to drive into how we decide what is the ideal or the optimum type of infrared to use in a line. Because a lot of times, any of the technologies will work exceedingly well. They will do incredible benefits to what you're doing. The optimization is based upon your business. That sometimes there's one technology that really sings out, and sometimes it's any of the technologies. Find a manufacturer that you trust and someone who you want to partner with, and you can make it work. So on buying recommendations, because this is kind of the end of this, convection, again, you can find, go to the PCI website. There's lots of people that, manufacturers who are members who you can buy convection from. Infrared is a much more specialized application. We work with a lot of convection houses that want to add infrared in. Infrared is, and all the other infrared manufacturers have been around a while. We all do this. So what you're always looking for is someone who's got knowledge of infrared, that's worked with it more than once, more than twice, regularly, does a lot of work. It's the same thing as selecting a doctor. You want somebody who's done this a lot. You want to test. So if it's a piece of sheet metal, that's pretty straightforward. We can look at a part and tell pretty much how it's going to operate. And in testing serves two purposes. One, it helps the oven manufacturer decide the best way to design a solution. And two, it's proof of concept for the end user to say, yes, this will work for me, and I'm happy with the outcome. So you get to see proof of concept in a way that is tangible. You can test it. You can do your scratch test. You can do whatever it is you need to do. You can see an oven profile test to see how fast did your parts heat up. You can hang the part differently and see how did that affect things. So you can do process testing. Any reputable oven, infrared oven supplier is going to be able to run tests in their ovens, in their lab, and be able to give you some kind of output. And that is a critical part of working with infrared. Infrared is not something that is one size fit all. If you walk away with nothing else, please know that infrared is much more of a specialty technology. That's one of the main reasons why it's not near as common as convection, because it is harder to work with. And it has more gears than convection, but you got to learn how to drive those gears, and you got to make sure you've got a right fit for what you're trying to do. So as we think about the, what do you walk away? Infrared will typically be, you're at a minimum, you're going to see twice as fast. And there are times we often see it's 10 times faster. See powder gel in seconds, 15 seconds, 30 seconds. Compared to what you see in convection, it's shocking sometimes. People don't actually believe it, that how fast it can work. Again, it has to work for what you're trying to do. But electric will always be the fastest. Catalytic will be slower, but cheaper. And convection will be substantially slower. So, those are kind of the value propositions as you decide what's going to work best for you. I've kind of said this, as I run through all of this, but it always, when people are asking for, what's the best, and the answer is always, it depends. And it's a frustrating answer to people that you can't say it's this or it's that, because there are no bad technologies, just bad applications. Because when a technology is misused, you can have a bad outcome. It can happen. And it has happened as the industry has tried to learn this technology, that 10, 20, 30 years ago, when, the learning curve was a lot steeper. There's a lot of good infrared manufacturers out there that are very experienced in this space and very reputable, and will ensure you have a good outcome to your process. So that is the conclusion of my speech. I went a little bit over where I wanted to, but I'm always gabby. Anybody who knows me knows that. But I guess, Kevin, it's back to you for questions.
Thank you, Marty. And I will say, yes, I have known you for many years. And yes, you can be gabby once in a while, but it was a great presentation, and I want to thank you for the time. We do have some questions from the audience here, so I'll just sort of read through them and let you go ahead and answer them.
Okay.
So the first question is, how do you use IR in curing 3D parts that are relatively non-uniform in their geometry?
Well, again, electric is probably not what you're going to choose. You're probably going to look at gas catalytic. And that's the reason I talked about conduction so much, because conduction plays an important part of the heating technology. So you've got conduction from the part heating itself, and conduction is accelerated by temperature. So since the catalytic heaters are going to be at a higher temperature than convection is, the conduction process is going to be much faster.
Okay.
And also your air, when you have air coming through the oven at 250 degrees or something, or whatever it may be, depending on the configuration, that helps accelerate the process as well.
All right. Can infrared be used as a touch-up out in the field?
Theoretically, yes. I mean, you've got different issues that you need to deal with. Portable heaters exist. You can do it in catalytic or electric. Electric, obviously, you have to have power. So with catalytic, you can do it with a portable tank, just like a barbecue tank. You don't typically see that because you get into other issues that can come into play on qualitative, because you still have to spray the powder and all that kind of stuff. So qualitatively, you don't see that very often.
Okay. Can an IR be used in a recoat operation?
Yeah. I mean, it's heat.
Okay. can you retrofit small conveyor ovens with catalytic IR? And he explains currently small steel parts are process convection conveyor ovens with 320 degrees C for 15 minutes. However, this is only accomplished at an inefficiently slow speed.
Right. Retrofitting ovens is, it depends, sorry. Depends on how the oven's designed. It depends on how much space there is. Sometimes it's not cost effective. Can it be done? Typically, always it can be done, or I'd say 80% of the time it can be done. But of that 80%, it depends on whether or not that's a cost-effective solution.
Okay. Does the quicker speed of gelling powder paint cause more orange peel?
No. It can, in that you have to apply the heat correctly, and there is a learning curve to that. Yes, you can burn parts with infrared. Absolutely, you can create new issues with infrared that you didn't have with convection. But that is where the control and learning the technology comes into play. Typically, we find after a couple of weeks, people have it all figured out.
All right. What is the working lifetime, gas infrared and electric infrared heaters, basically in working hours?
Oh, God, I hate this "it depends" answer, but it kind of is. In catalytic, it's a function of how clean your plant is. So if you have a lot of free dirt rolling around in your plant or powder migration, you're going to contaminate the heaters and you'll have to have them rebuilt. Catalytic heaters, I have seen them have to be rebuilt in a year in an incredibly dirty environment that they really weren't, they almost sprayed the heaters. And I've seen them go as long as 15 years. That typically is too long. 7 is about the average, but they can be rebuilt multiple times because there's no moving parts in a catalytic. In electric, in bulb, when you're done, you're done. When they're out of life, they're done. You have to replace them. Some electric resistance can be repaired in the field. Some cannot. Typically, the shortwave bulb has the shortest life, and electric resistance, depending on how it's designed, and you can typically see a 10-year lifespan. Okay. But ours is kind of a difficult thing because everybody operates differently.
Okay. Do you have an opinion about the relative maintenance costs for infrared versus convection ovens? Does infrared panels require cleaning at the same frequency as a convection oven?
Again, it depends on how dirty your plant is. Catalytic, we do suggest cleaning, but it's a fairly quick process. Whether you do it once a year, we would certainly recommend you do it at least once a year, but you don't need to do it monthly, typically, unless you have a very dirty environment. Electric, it's the same kind of thing. Powder migration will affect electric. When you get into reflectors, if you do not keep your reflectors clean, they become absorbers. And that is an issue because you've now created what was supposed to be reflecting the energy into the part has now absorbing the energy, and it's not getting back to the part. So the reflectors can sometimes be more critical actually than the heater themselves. But maintenance is typically a function of how clean, if you don't do good maintenance other places, you're going to have the maintenance problem in any piece of technology you have.
Okay. What is the best way to establish a thermal profile using a data pack for a catalytic, gas catalytic?
Well, typically you're gonna, each part is different as to where you would locate it, but typically you're going to put 2 to 3 probes on each part when you run it through an oven, and you're looking to see how the curves, come out. Okay. I'm not sure if I understood the question. I'm not sure if I answered it correctly, but.
Okay, well, I think that's what he was after, but
okay.
It's pretty much the same as a convection. You're just going to run through it the same way.
There's no theoretical differences between how you run an oven profiler between infrared or convection.
Okay.
You're trying to get to the same output, a hot part.
Sure. Are fans ever used to promote airflow in an IR application to promote heat transfer?
Absolutely in catalytic, typically not in electric. Electric sometimes has small air movement, but by orders of volume, catalytic, absolutely. Not always. You're not going to do it in a boost typically because you don't want air movement in a boost.
Okay. Do the IR settings need to be changed depending on the color of the powder?
Typically, no. But the higher temps become more sensitive to color. So again, it's a function of some powders do react a little differently. That's again the reason you should test. I have seen on a rare occasion, we've seen a powder that is not like infrared a whole lot. Doesn't happen very often, but it has happened. I think most of the powder manufacturers know how much IR is out there, so they design for that. But typically you don't. But let's put this a different way though. If you're doing all white light parts and then you're doing heavy black parts, absolutely you're going to use a different recipe. But okay. White to black itself, typically not on the same part.
All right. How can the cure cycle be so short and achieve the proper time at temperature the manufacturer suggests?
Because what those times are, and I've talked to a lot of powder manufacturers about trying to create infrared profiles on their powders. All you're trying to do in the powder is get it to activate and gel. That's what they're saying is at this temperature in a convection oven, this is how long it takes. This is the result. So that's the recipe. The powder doesn't care what technology is doing that. The same way if you drive to the grocery store and you drive at 10 miles an hour versus 100 miles an hour, you still got to the grocery store, but you just got there a lot faster. The powder doesn't care. So it activates and gels and goes through its process of curing.
All right, here's a question. I believe it's referencing the response time. Is what is the difference in startup time for gas catalytic versus electric? Like first morning starts,
Well, most ovens can have a cycle designed into the PLC to start that before you're ready to run operating. But catalytic typically needs a minimum of 20 to, and sometimes people overdesign, not overdesign it, but for a safety factor to make it 30 minutes of startup time because the catalytic pad must get to temperature before the natural gas is allowed to come into the heater. That's where the safety factor comes in. Okay. So you're typically going to have a 30-minute warm up in a catalytic oven. In a electric oven, like any oven, because of the conduction, the whole oven is going to get hotter through the day, but you're going to be hot in an electric oven and you're going to be ready to powder coat a part in a minute.
All right, and this one is sort of related. Is there an issue with starting and stopping the conveyor and turning the temperature down in order to allow for a better conduction, electric IR?
Well, starting and stopping the conveyor has its own issues that we won't address, but certainly people slow down their conveyor when they have a heavier part coming through and they want to give it a little bit more time in the heated length. So yes.
All right. How do you determine the correct wavelength for wood MDF parts?
Oh, there's lots and lots of tests out there that a lot of people that are specializing in this space are doing. And the jury is still out as to the optimum wavelength. It depends on the species. There's a lot of things that factor into. Catalytic is very, it is the most common technology in that space right now. Electric is being used more and more. But catalytic is in first place right now. It remains to be seen, but again, different lines require different things on what you're trying to achieve. It is my view that medium wave electric will also be part of the solution.
Okay. What are some of the advantage or disadvantage of using IR in a batch paint process instead of using a conveyor?
You don't see infrared as much in batch. It's harder to work with in batch because, you know, if you have a batch cart that you're going to put in, you can't really use that. You can do batch operations in infrared very easily, but you're not going to mix and match your parts unless you are putting in one rack at a time. You can't do the multi-layer deep.
Okay. Here's, I believe I know the answer, but I'll ask it. What's the cost difference, or is there a cost difference between IR curable powder and normal convection powder?
There is no, they're all the same.
That's what I thought. So, okay. If an IR oven has a bottom panel under the parts, do you risk premature contamination by powder falling onto them? And if so, how do you tell when your panels are working optimally?
Well, everybody who has an infrared oven should have a heat gun. You should have a heat gun anyway. You know, look at the operating temperatures by manufacturer's spec of what that part was designed to do, or you know what that panel was designed to do. And when it starts changing, you know, you may have a problem. You'll start to, in catalytic, you'll start to see it get splotchy. You'll start to see you just can't get the parts the same temp that you could before. Electric's real obvious. It just doesn't work. It shorts. It, you know, it's very black and white when electric isn't working right. Catalytic is much grayer. As to a heater on the bottom, that can be an issue, but typically you should be gelling it fast enough where, and you have your still zone where powder is not, shouldn't be falling off the part in a properly designed infrared oven, because you should be gelling it fast enough that it's already sticking to the part.
Yeah.
And you shouldn't have air in that gelling section.
Okay.
Typically don't.
All right. If I gel in convection, is the part done activating?
That's the idea. I mean, that's what you're trying to do, is to get the powder. Sometimes people just need it to gel to the point where the powder doesn't fall off. You don't have to actually get to a gel. Ovens are designed differently depending on, again, what you're trying to achieve.
All right, we've got just a few minutes left here. I'm not sure you'll be able to answer this one straight out, but if not, we can figure out a way to get information to them. Gas infrared per square meter and power versus electric medium wave infrared per square meter power. I think it's power input.
I have some information on that. I would have to send that to you because that's a complicated answer.
Okay. Well, I guess whoever is that, if you look on the screen, there is Marty's contact information.
Yeah, so, email me.
Yeah. All right. Other than that, that is the last of the questions that I have in for here. And if you would, Marty, please slide to the last slide there. I just want to take this time then again to thank you for joining PCI for this webinar, and I want to thank Marty for presenting it. It was well done. They still be available to see the webinar on the powdercoating.org website. It'll take about 5 to 7 days to get us up there. Also, don't forget to save the date for the Powder Coating Week 2021, which will be in Orlando this year, February 23rd to the 26th. We have a great slate of presentations planned. Should be a great event. And I just want to again thank you, Marty, and everybody. Have a great rest of your day.
Thank you.
Thank you.